This mechanical system's always losing accuracy.
Yep, so we are recording. So let's go ahead and talk about the practice exam first. The practice exam is actually the exam from last semester. So there will be some changes for this semester. I'll tell you guys exactly what those changes will be as we go over the material. So if you go to propositional logic, there are several practice exams in that particular section. Let me just zoom in so we can see a little better. So in here we have exam 1 practice questions. We have actual exam 1 from spring 15 and also 2016 spring actual exam 1. So I'm going to use this one, at least to start with, because this is the actual exam from last semester. The amount of time is the same, even though we have a different start time for this semester. So we still have 80 minutes for the entire exam. If you finish early, you can leave the classroom if you want to. There's no need to stay in the classroom. The room number obviously is not going to be the same. This is room 157. The exam is still open book and open notes, but no electronics. Okay, I know that several of you have your own devices. So if you want to bring some additional material, you will have to print it out first before you can use it during the exam. The exam is an individual assessment, which means that the score should reflect the competency of the student with the name and student ID as indicated in the exam itself. So the first thing you want to do is to make sure you write down your name. And I would like you to write down your family name, surname, last name first, and then your given name or first name, okay? Because this is how the student, this is how the roster is arranged. So this makes it a little bit easier for me to grade and enter the scores. I would also like you to enter your student ID or the student ID number. So if you don't know it at this point, you might want to learn what it is or bring a sheet of paper to remind yourself what your student ID is. Answers should be independently and originally derived in the allotted time frame, observing all the rules applicable. So just the basic stuff, I don't think there are any surprises here. No sharing of open book notes material during the exam. So that means, even if your neighbor is asking you, hey, can I borrow that piece of note from you? You have to say no. And it also means that if you think that there will be something useful to you during the exam and it's on a piece of paper, bring it, okay? You don't depend on somebody else to have it because they cannot share it with anybody else. And do not talk about the answers or the questions with students who may not have taken the exam or who are taking the exam. Use additional sheets of paper if that is necessary. Okay, so I would like you guys to bring additional, just binder paper is fine, blank paper is fine, just some additional sheets of paper, just so that if you need some additional space, you have the room to write it and I can staple everything together. Because this is an open, these are all open-ended questions, so you need to kind of write in a legible way because, if I cannot read the answer, I cannot give you points. So you got to make sure it is legible. The questions are weighted, so that means not all questions have exactly the same weight. The first thing you might want to do is to just get a really quick glance over to look at all the questions and pick out the ones that you think are the easiest one to answer first. So that's a general strategy for any type of exam, is to answer the easy ones and then you work your way to the more difficult ones. And the reason for that is because I don't want you to waste a lot of time on a really difficult question and then have no time left for the easy ones. Okay, so you definitely want to spot the easy ones and go like, yep, I know that one, I know that one, I know that one, and then kind of go back and work on the more difficult ones. This exam accounts for 20% of your final grade, so it's not a whole lot, but it's not really small either. So that's. Are there any questions about just the beginning part of the exam? This is from the previous semester. No questions, so we're going to move on to the questions. The answers are already here, so it's kind of a little bit harder for me to show you the question without the answer. Okay, so question number 1 is asking show the elements of X assuming it is defined as follows. So the definition is really just testing whether you understand the concept of union and also the concept of having a set inside another set. So in this case, we have a union of several things. Okay, we can do this. So I can use mouse pad to cover up part of the answer. So this way we can just work on it. There we go. Okay. So when you look at the union, okay, you have to make sure that we end up only with unique elements. The first set only has an element of 1, so that has to be included in the final set, in the union. The second set has a set of 1, but that is considered different from just 1 itself, so that's why the set of 1 is an element of the union. Okay? Are there any questions about this part? Because this is the one part where some people have questions about. And then the next one is a set of the set of 1. So once again, that is also considered unique. So the element in the final set or the union is the set of a set that only has 1 as an element. And then the next one is a set of 1, 2. Okay, but this one, okay, this one here is the same as this one here. So in the end, I only need the 2 out of this set here. And this one is considered completely unique because it is a set of 2 elements, 1, 2, which is completely different from the set of 1. So that's why it is unique and it is by itself. So this is the final answer. The answer is you have a set of 5 elements. The first element of X is 1. The second element itself is a set. It is a set of 1 as an element. The third one is a set of 1 as an element. The fourth one is 2 by itself, and then the last one is a set of 1, 2, and that entire set is an element of X. Are we doing okay so far with these concepts? If you think about a set as a folder, then it starts to make sense. Because a folder that contains another folder that contains a file is not considered the same as the file itself. So that's one way to kind of quickly remind yourself, what do I do when we have a set of a set? Well, it's almost the same thing as a folder with a folder. So when we count the cardinality or the number of elements in this thing, there should be 5 because we have 1, 2, 3, 4, 5 distinct elements, and that is the case as well. So I'm just using mouse pad to hide the solution so that we don't actually see the solution as we work on it. Okay, question number 2. Question number 2 is really easy. What is the Cartesian product of the set of 1 times the set of 1? That's a pretty easy one. Well, the easy part has to do with, we know the only element is 1, 1. Okay, so there's only one element in the Cartesian product. Okay. Are there any questions about number 2 so far? No questions? Okay. Moving on to question number 3. Okay, question number 3, there are several ways to approach this. You can approach this by the definition of the operators, of the set operators. You can also look at this using Venn diagram, using a pictorial way to look at this. It's up to you. Different people work on this differently, so it's entirely up to you. If you want to work on the semantics, which is basically just the meaning of minus in the context of set, the first one is A minus B, which is everything in A that is not found in B. The second one is B minus A, which is everything in B that is not found in A. So somewhat intuitively, they do not share anything because in the first one we only have stuff that is in A but not in B. And then the second one, we have stuff that is in B but not in A. So when you look at the intersection, which are the things that are common to both of those things, A minus B and B minus A, there should be nothing in common. So that's kind of an intuitive way using the semantics of the operators to approach this. The other way to look at this is to use a Venn diagram. I'm switching to a document camera, and because I'm just going to draw some pictures here. Okay. So when you look at a Venn diagram, and you look at the two sets A and B, okay, A minus B is representing everything that is in A but not in B. Okay, so that will be this portion here. This is representing everything in A but not in B. Okay, so I have to make sure that everything in between here is not shaded. But then the other one, okay, so this part is A minus B. And then when we look at B minus A, we're looking at, I'm shading it slightly differently just so that we can see which part is B minus A. So that's B minus A. And you can see that these two do not share anything. They do not intersect. And that's why the intersection, which is the inverted U symbol, is empty. It's an empty set. So are there any questions about this one? No questions? Okay. So it all depends on how you normally think and how you normally learn. If you're visual, a picture would help. If you are more of a semantic type of person, just looking at the definition, then just reviewing the definition of the minus symbol is going to be helpful. All right. So moving on to the next question. Next question is number 4. Okay, number 4 is asking, given that f is a function that maps from a domain D to a codomain E, indicates properties of f that has to be true. Okay, this is not something that can be true, but it has to be true because of certain properties. For each case, I'm going to show you the table. Because of the conditions stated in the table, it is okay to say cannot tell when you cannot really say, well, given this is what we know about the domain and the codomain, I cannot tell whether it is going to be surjective or not. It's okay to say you cannot tell. So let's take a look at the table. The condition is this. So I'm going to overlay my editor over that so that I can just go ahead and write the answer here. Okay, so the condition is this. Okay, if you know that the cardinality of the domain is less than the cardinality of the codomain, what can you say about the injectiveness of the function? Or can you say anything about the injectiveness?
Have to be right.
No, you cannot tell. You cannot tell because you can think of extreme cases of not injective. The extreme case of not injective is having everything in D mapping to the same element in E. It is allowed, okay? But that would make it non-injective. Okay, so injectiveness is cannot tell. Okay, I'm going to write the header here. Injectiveness is cannot tell. What about surjectiveness? Okay, so there are 3 possible answers to each cell. You can say cannot tell, like that one. You can say definitely not, or you can say definitely yes. Okay, so those are the 3 possible answers. What about surjectiveness? Surjectiveness is basically saying, are we using up everything in the codomain?
No.
We're guaranteed not to be using everything in the codomain. There's no way we can, because we have fewer elements in D than there are in E. Okay, so we're definitely saying it is not the case. And the last one is bijectiveness. Bijectiveness. If any one of these things is a not, then bijectiveness is definitely a not. Okay. All right. So moving on to the next one. The cardinalities of these two are exactly the same. Can we say for sure that they are the function itself is injective?
No.
Nope. Cannot tell. Right. Can we tell whether it's surjective or not? Cannot tell. It can be surjective, but it's not surjective for sure. Okay. Can we tell it is bijective? Well, since we cannot tell in terms of injectiveness and surjectiveness, then the only thing we can say is say cannot tell. And then the last one is saying that we know the cardinality of the domain is greater than the cardinality of the codomain, but in terms of injectiveness, we know that it is not, okay, for sure. Because in order for a function to be injective, the cardinality of the domain has to be less than or equal to the cardinality of the codomain. Because each element in the domain has to map to something unique in the codomain. Okay? But because in this case we have the domain, or the cardinality of the domain greater than the cardinality of the codomain, it cannot possibly be injective. Okay? There's no chance it can be injective. Because based on the pigeonhole principle, okay, remember the pigeonhole principle, based on the pigeonhole principle, we know that at least one element in the codomain is mapping from at least two elements in the codomain, just because of the pigeonhole principle. Well, what about surjectiveness? There's no way we can really tell, because everything can still map to one single element, leaving everything else in E not mapped. So we cannot really tell whether it's surjective or not. But because it is for sure not injective, it cannot possibly be bijective either. So we can say that it is definitely not bijective. So is that okay? Are there any questions? Yep, go ahead.
How could it be surjective if the domain's bigger than the codomain?
If something needs to be surjective, in order for something to be surjective, the cardinality of the domain has to be greater than or equal to the cardinality of the codomain. Yes.
Okay, because they could map to more than one. Okay.
Yep. But just because the cardinality of the domain is greater than the cardinality of the codomain does not guarantee it is surjective. Because you can still end up with a situation where everything maps to the same element in the codomain, so everything else in the codomain are not used. All right, so let's check the answers here. Yep, so that's exactly what we just talked about. Okay, moving on to question number 5. So let me do it this way. Okay. All right, so question number 5 is asking you to describe function f, and in this case I use false true. Oops, that was not intentional. I scrolled the mouse unintentionally. Okay, so in this case the domain is the Cartesian product of true false and true false. In other words, the parameters to f, there are two parameters to f. The first one is either a true or a false. The second one is also either a true or a false. It maps to just true false. And I want f of xy to be the same thing as x implies y. And I want you to describe whether this function is surjective, whether it's injective, and whether it's bijective. What do you think? Well, first of all, we can actually do the entire mapping and find out, whether it is to find out exactly how the mapping works. So, which is what I'm going to do next. Okay, so this is f. F is mapping from 0, 1 times 0, 1 to 0, 1. But the actual definition is a set of two tuples. And the first tuple of the two tuple is a two tuple itself because it is an element of the domain. So we now say, okay, what is false implies false? What is the true false value of false implies false?
True.
It is true. False implies false is true. What about false implies true?
True.
That's true as well. What about true implies false?
False.
The answer is false. And the last one is, what about true implies true?
True.
That is true. Okay, very good. Okay, so now we know the exact mapping between the domain and the codomain. So now let's go ahead and answer the questions in terms of surjectiveness, injectiveness, and bijectiveness. Is it surjective? In other words, is everything in the codomain used?
Yes.
Yes, because both false and true are used in the codomain. So the answer is yes to surjective. Is it injective? Cannot possibly be injective. It cannot be injective because your domain has 4 elements and then your codomain only has 2 elements. So it cannot possibly be injective. But because it is not injective, it is enough reason to say that it is also not bijective. Are there any questions about number 5, at least at this point? Yep.
So you're able to just make that mapping up however you want?
No, it's not however I want. Because I define the function to be implication based on the question. because the way I define it is I want f of xy to be the same thing as x implies y. But x implies y already has its own truth table, so I'm just, I'm changing implication from an operator to a function, but preserving its meaning. It's just a different way of looking at it. Yep.
Can you remember why that's not injective again?
It is not injective because the domain is the Cartesian product of true false and true false, which means there are 4 elements in the domain. But the codomain is only true false, which only has 2 elements. So from the previous question or the discussion of the previous question, whenever the cardinality of the domain is greater than the cardinality of the codomain, it cannot be injective. So only because of that I know it's not injective already. I don't even need to know how the function is actually defined. Okay.
Oh, I see what happened. You map the cross product to use it.
Right.
And you map it using the implication.
Yes, that's how I define the function. So so f of xy is really the same thing as x implies y. But instead of looking at implication as an operator, I just look at it as a function. Okay?
So the tuples as elements, you're looking at both.
This is coming from the domain, and this is coming from the codomain.
So, well, I guess what I'm wondering is
this is our domain, and this is our codomain. In other words, this has to be an element coming from here, and this has to be an element coming from here. Yep.
So is that tuple x in the domain?
Yeah, x is in the domain. No, x. Both x, y are the tuple to x, y is in the domain. Because we are taking x and y together as the parameters to f, so that makes it the domain.
Oh, okay.
So when you write a function, when you just write a function casually, and you say f blah 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 blah, okay, if you have 4 things inside the parentheses, then your domain is going to be the Cartesian product of whatever set this comes from times whatever set this comes from times whatever set this comes from times whatever set this comes from. So that's basically the same thing, except in this case, x is just true false, y is only true false. Any questions about this one? Okay, no further questions. Okay. And question number 6. Okay, so number 6 we kind of talked about it already. In propositional calculus, as discussed in class, 1 is an element of which 2 sets. And we talked about this in the previous class because somebody asked about this particular question. So it is both in A and I. But the reason is different. Okay, the reason why it's in A is because it is a symbol. Okay, every symbol other than operators have to be found in A. Okay, in alpha. But it is in I or iota because it is initially true. It is by definition true, and that's why it is in iota. So it's in both of these sets, but for different reasons. Question number 7 is a proof thing. This is not something that I want you guys to do for this particular test, but just in case we want to do it, let's go ahead and just see how we can do this. So the question is, how do we prove that false is not true? Now it looks really, really obvious, right? Because we know that by definition, not true is false. But how can we prove that false and not true are exactly the same thing, but only using using not resolution, but only using the algebra, the axioms of Boolean algebra. So these are the axioms of Boolean algebra, And you can see that nowhere in here does it say anything about not false is true or not true is false. So the way we prove that is we start with this one here. Okay, so I'm not sure whether you guys can read this part. Let me zoom in a little more. There we go. One more time. There. So the first step is to show that false is P and not P. Now how do we know that? There's one thing that says right here. Okay, so 1.7 says anything and the negation of that anything is false. Okay, seems pretty easy to do. And then we can say double negation of that. Now double negation is 1.5. So if you take the double negation of something, you get that something back. Is that okay? All right, but how is that going to help us? Well, we use this one here. We basically use De Morgan's law to distribute the inner negation into the inside first. So this is the application of De Morgan's law. De Morgan's law is stated here. 1.4. Yep. So one of these two, there are two versions of that, but one works on the conjunction in the inside of the negation, one works on the disjunction inside the negation. So that's De Morgan's law. So after you apply De Morgan's law, then you apply the double negation again on this particular double negation. So you end up with just P. But then you can use the OR 1.6 to show that not P or P has to be true. And then because that is just true, then you end up with not true. So now we end up with false is not true, but using only the axioms. Okay. So here's the question. If I were to ask you to prove this in a test, okay, you're under pressure, you only get 2 hours, 80 minutes to work on this entire thing, this is going to be pretty hard to do. Because there are many ways you can apply the axioms, but most of those ways are moving in the wrong direction. Okay, you're applying the axiom correctly, but it's not leading to the solution. And that's the problem of mathematical proofs in general, is given any type of statement, you can apply axioms. There are many axioms that are applicable. The question is the application of which axiom is going in the right direction. That's the question. Is that okay? How does this relate to resolution, which is your next homework assignment?
You only have one.
You only got one rule to apply. And can we end up applying rules in the wrong direction forever and just leading us further and further away from what we want to prove? Not with resolution. Resolution has to terminate. And that's the beauty of resolution, and also proof by contradiction. Those things, they all work hand in hand. There's only one thing you have to apply. Do you have to choose? Yes, you do. Okay, because you have to choose which two sub-expression to resolve. But that choice is mechanical because you're just looking for one that has a variable, another one that has the negation of that very same variable. You resolve that and see if you're adding any new term to the whole thing. Okay, so it's very mechanical and it has to terminate. So that's the reason why we like resolution, because we don't have to think about which axiom out of 12, these are 12 classes of axioms, okay? Some of these have multiple ones inside the class too. So this is the reason why we like resolution. I just want to use this opportunity to point out, the application of resolution is extremely, extremely mechanical compared to what we're doing here. Question number 8. Question number 8, oh, okay. That's, I need to, can't scroll and hide at the same time. Now we can do sort of that. There we go. Okay, so I want to use a truth table to prove that P and, in parentheses, not P or Q, is the same thing as P and Q. But this time I don't want you to I don't want to use resolution. I don't want to use Boolean algebra. I just want to do it another way, which is also really easy in Boolean algebra. Use a truth table. Okay. So the way we do this is to fill up the truth table. Okay. Now P and Q are the variables, so they only start with certain values. Okay. 0, 0 is one way to start. 0, 1 is the next one. The next one is 1, 0. And then the next one is 1, 1. Because P and Q are both Boolean variables and they're independent from each other. So this is how we can generate the first part of each row of the truth table. So the rest is really just evaluating that expression and say, okay, is the expression true or is the expression false based on what we know about P and Q of that particular row. So in this case, P is false, so not P is true. We don't even need to know what Q is. Okay, so this is true. This one is true for the same reason. And then this one is false because P is true, not P is false, but Q is false as well. So we have false or false. And then the last one is true because they're actually both true at the same time. Nope, take it back. But one is false, but the other one is true. So we're good there. Okay, so this one, with this one, we are just adding P and then the previous column. Because we have P being false here, the whole thing has to be false. Same reason this entire thing is false on the second row. And on the third row, we have not P or Q itself being false, so the entire thing is going to be false. But on the last row, we have P being true, but not P or Q is true as well. So we have the conjunction itself being true. So now we have just the conjunction itself. So the conjunction itself is easy to work with. 0, 0, 0, 0, 1, 0, 0, 0, 1. That's the truth table of conjunction. So now you look at the second last column and the last column. They are exactly the same. And in Boolean algebra, this is good enough as a proof to show that these two expressions are truly equivalent to each other. Are there any questions about number 8?
Why were they the same? Because the last two?
Yes, because for any combination of true false values of PQ, these two expressions will give you exactly the same answer.
Oh,
The last two columns,
Okay,
right?
I was thinking rows.
Oh,
You can use
yeah.
resolution
Did I?
on that one too.
You can probably use resolution on that too.
P&1,
Hmm?
P&1.
P and 1. But this is not P or Q. It's not P or P.
And not P or Q.
So if you use resolution, you will have to
There's already CNFs, right?
well, if you use resolution, this becomes a theorem, right? Because you have to negate the theorem, combine it with all the known stuff to prove that it is true. Mm-hmm.
If you were to prove the implication is what it is using the same way, and you get two different truth tables, are they supposed to equal the same like they did here? Is that how you prove it?
You mean turning this part here into implication?
Right.
Well, it is the same thing as implication because implication by definition is P implies Q by definition is not P or Q. So it would give you identical results.
I was trying to do the assignment, the CNF assignment,
Mhm.
and that first part I was trying to prove that
Okay.
it's the implication, and
Well,
I
once-
ended up with two different truth tables.
I
They
see.
were identical. So is that enough to?
For the homework assignment, for the homework assignment that's due today, there's nothing to prove. All I want is for you to give me the CNF of the entire thing. But you don't have to do any resolution. There's no proof by contradiction. The homework assignment that's due on Monday is the one where you have to apply resolution and proof by contradiction. So we'll get to the homework assignment because I want everybody to have a starting point for the second part of the homework assignment. So we only got one question to go, I think. You only got one more, which is question number, we got two more. So question number 9 is about relations. And the question is, okay, here's the question. So the question is, we have R1 as a relation. It's a relation that is applied over integers. And it really is just less than. So, Z, X R1Y means X is less than Y. And then R2 is greater than, okay? So when you look at this, okay, so the first thing we want to do is to say, okay, but what exactly is a relation and how do we apply that here? So let's go ahead and do that. Well, we can do this part here, just like that. So R1, can be defined as a set, okay? And it's a set of two tuples because it's a relation. So we are trying to figure out, okay, we have to pick the first number from integers. We have to pick the second thing from integers as well. But we want the relation to be true because that's what we keep in the relation is, when it is true over, these specific elements. So pick two integers where the first one is less than the second.
1 and 2.
Okay, 1 and 2 is 1. Okay, so 1 and 2 is an element of the relation. Pick another one. -2 and 100. I'm just picking some really random cases here, to prove the point. Okay, 0 and 1, -4, -3, and so on. This is how you define a relation. It is a set of two tuples where the relation is true. Okay, how you relate the two elements. So the other one can be defined pretty much the same way, except this one is greater than. So I can pick 200 and 0 as one. I can pick 45 and 42 as the other one, and so on. Okay? So the question, however, is to say, okay, are these reflexive, symmetric, transitive, and also equivalent? Okay, so for each one of these four attributes, tell me whether R1 is reflexive or not, tell me whether R2 is reflexive or not, and so on. So let's go ahead and make a table out of this thing. So we have R1, R2, R1, well, they're the same. Okay, so I just need one single thing. So we have reflexive, symmetric, transitive, and finally equivalent. There we go. Okay. Is R1 reflexive? In other words, given x is an integer, is it true that x is less than x for all integers? No. Then it is not reflexive. So remember, reflexive is reflecting the self. Okay, it's not the same thing as symmetric because it sounds like symmetric, but it's not. Okay, so we know that R1 is not reflexive, which automatically means it cannot be equivalent because you need all three to be equivalent. Okay, next question is it symmetric?
No.
In other words, when you have symmetric, it means if x is less than y, then y is less than x. Is that true? Nope, it doesn't work for less than, so it is a no for symmetric as well. Is it transitive? If A is less than B and B is less than C, does that imply A is less than C?
Yeah.
That works. So that's how we fill in these attributes. Greater than is exactly the same way. Okay, it's just in the opposite direction, but it is the same. So now we define R3 to be the union of R1 and R2. Okay, so the first question is there a common name, an easier name for R3? Instead of calling R3 the union of the relation of less than and the relation of greater than, is there a more common name for R3? R1 handles all the less than or equal to, less than or greater than.
I said not equal to.
Not equal to. Okay, not equal to is correct. Okay, so R3 being the union of R1 and R2 is really just not equal to. Okay, so knowing that R3 is not equal to, then we want to find out these four things about R3. So we'll just add it here. Okay, with R3, is it reflexive? X does not equal to x for all x in integers. That's not true. Okay, because x does not equal to x is not true for any integer in the set of integers. So it's definitely not reflexive, which also makes it not equivalent. Okay, but is it symmetric?
Yes.
It is symmetric because if x does not equal to y, then y does not equal to x. It is symmetric. Is it transitive? If A does not equal to B and B does not equal to C, does that imply A does not equal to C?
No.
That is not the case. Okay. So that's the answer for question number 9. Are there any questions about question number 9? Yep.
How did you know R3 is not equal to?
Because it is less than or greater than, basically. Because we have a union of R1, which is less than, and also the set R2, which is greater than.
So there's no way it could be equal.
It cannot be equal to because, you know,
Covers the equal.
hmm?
You have to cover the equal.
Exactly, because R1 does not contain the equal to relation, R2 does not contain equal to either. So when you look at the union cannot have that either. But it does contain all of the other cases, all the not equal to's.
Oh, okay.
Yep.
Do transitivity and symmetry imply reflexivity? Because you could have ARB, and that implies that BRA, and then if it's transitive, that implies that ARA.
I do not think that is the case, because if that were the case, they would not have 3 separate attributes. So your question is asking whether being symmetric and transitive at the same time implies reflexive, right?
Yeah, but it could be an empty relation. I guess that's it.
Yes.
I guess that's the only other case is when ARB is never true.
Yeah, because reflexive has to be applicable to all elements in the set. So that's why you cannot, the implication does not work. Yep.
So, for transitivity's sake, so we're in one we would have, say, 1, 0 as a tuple, and in the other one we'd have 0, 1 as a tuple.
Not exactly. Let me just kind of show you guys the definition of what is being transitive. Okay, so being transitive means this expression has to be true. So we are talking about a R over a particular set X. Okay, so I'm not even talking about integer, less than, greater than, or anything like that. Okay, we're just talking about a relation R over X. So in order for this R to be transitive, the following statement has to be true. So I'm going to use a shorthand here. I'm just going to use a shorthand of A, B, C are all elements of X. So instead of separating each element of, I'm just combining all of these. Okay. So this part has to be true. So what needs to be true is A implies, ARB and ABRC has to imply ARC. This is the definition of something being transitive. What if ARB is not true? Well, don't even bother to figure out whether ARC is true or not. What if BRC is not true? Don't bother to look at the second half. But if you can find elements ABC such that ARB is true, BRC is also true, then we want that to imply that ARC is also true. Now, why is not equal to not transitive? Well, it's pretty easy. You pick A to be a 1, you pick B to be 5, and then you pick C to be 1 again. Then you can see that it is not transitive, because A does not equal to B is true, right? B does not equal to C is true. And note that over here, there's no restriction that A and C cannot be the same thing. So A does not equal to B is true, B does not equal to C is true, so this conjunction is true as well. But then when you look at A does not equal to C, that is not true because A and C are exactly the same. So A does not equal to C is not true. So this implication does not work anymore because now you have the first part being a true, the second part being a 0, which means the entire implication is false. And since I can find one counterexample, that means it doesn't work, because this particular implication has to work for all possible ways to choose A, B, and C. Is that okay? All right. Okay, so getting back to here, we have one last question. The last question I think it stumped some people last time. The last question is asking, describe a bijective function. Okay, in other words, I want a function that is both injective and surjective at the same time, okay? And I want to map the Cartesian product of natural numbers, and natural numbers to natural numbers. But I want this to be bijective. So the question is, how do we do this? Instead of doing this in closed form, define the function as a set of two tuples where the first component itself is a 3-tuple. Give me an example of the mapping of the first 10 3D coordinates to natural numbers, 0 to 9, and here's an example, blah, 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 and so on. Okay, so how do we do this? Remember, it's open book with notes, right? So when was the last time you saw something like this, mapping folding dimensions?
Cantor, diagonals.
Right. Okay, so we looked at that one the first time, right? You guys do remember this? You know, we basically looked at this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Got that one? Okay. So this question wants you to give me the first 10, but I want to do it in reverse, okay? But this doesn't tell us how to do stuff in reverse, or does it? So the way you do this is you apply the inverse, and then you apply the inverse one more time. Okay, let me show you what I mean by that. And I'm going to use the document camera to do this because it's going to be recorded. There was a question? Nope? Okay. All right. So let's go ahead and do this. There we go. Okay, so what we want to do is to figure out the whole thing backwards. Because f itself is mapping natural number times natural number times natural number to natural numbers, right? And I want you to do this kind of backwards because I want to know how the first 10 natural numbers from the codomain correspond to 3D coordinates. That's what I want to do. Okay. So what I do need is to figure out, okay, let's figure out this part here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, there are 10 numbers because I start counting from 0, so now we have 10 numbers. But it's not 3D. This is only 2D. Well, it's okay. Let's deal with 2D first, okay? So when we look at this as 2D, okay, so we have n here, and then we have n times n over here. So now we have the specific elements from n, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm probably not going to do all 10 numbers because the approach is the same. But then you just look at this and go like, okay, 0 is corresponding to the coordinate 0, 0. 1 is corresponding to 1, 0, because this is x and this is y. And 2 is corresponding to 0, 1. 3 is corresponding to 2, 0. 4 is corresponding to 1, 1. 5 is corresponding to 0, 2, and so on. But text, this is not quite 3-dimensional. It's only 2-dimensional. So what can we do about this part? Come on, you guys know the answer already. You just need to reverse it one more time. Okay? So you look at this number here and say, I wonder what I can do with that 0. So you look up this table again and say, oh, 0 is mapping to the coordinate 0, 0. So now you can say n cubed, right? I just don't want to type n times n times n. So now this can become 0, 0, 0. And if you want to, you can put parentheses, extra parentheses around those two. Oops. Shift. There we go. There we go. Okay. And we can do the same thing about this one. So now this one becomes 1, 0, 0. What about this one here? We keep the first number, but then we look up the table and find out, okay, what is 1 corresponding to? 1 is corresponding to 1, 0. Okay. And what about this one? It's 2 and then 0, 0. This is 1, 1, 0. and this one is 0, and then 2 is over here, which is 0, 1, and so on.
You can do it again too, right?
Yep.
Yeah.
Yep. So you can unfold space, using this little lookup table. That's basically what the question is asking. Even though in my notes I gave you the closed form, which involves like n times n plus 1, and then the whole thing divided by 2, and then the whole. You don't even need to do that. You just need to figure out what is the first 10 numbers, and then just use it twice to unfold single dimension into 2 dimension. Is that okay? All right. Yep. Question?
Can we see the answer?
The answer, I may not have an actual answer here. No, this one does not actually have an answer, because I think in class I was also just using describing the answer on the whiteboard.
But that's the correct syntax.
That is the correct syntax.
Okay.
Yeah. So in this case, in our case, if I want to submit the actual answer, it's going to be G is going to be a set, and then what you do is you basically just map all of these. Okay, let me see which one is good. Yep. Okay. So you're basically just mapping 0, 0, 0. Whether you put extra parentheses is up to you. Map it to 0. That's the first 2 tuple. And then the next one is 1, 0, 0, mapping to 1. And then the second one, the next one is 0, 1, 0, mapping to 2, and so on. It's just looking up it's basically looking up this thing twice. All right. We got about half an hour left. So let's go ahead and talk about the solution of the homework that was due today earlier, and so that we all have a starting point for the next homework assignment. If you have any further questions about the exam, go ahead and ask when you do have the questions. So I'm not, saying that you cannot. Yep, go ahead.
Is the exam going to go up through resolution?
Yes.
Okay.
So this exam is going to go up to resolution, which means it is a little bit, in terms of scope, it's more than the exam from spring semester. But I'm not going to ask the actual proof by axiom question. So instead of using that question, I'm going to use resolution.
Okay.
Which I think is easier in many ways. Once you understand what is resolution, it's actually easier than proving by axioms.
But it'll be none of the statistics that we started on Monday?
No, the probabilities and the combination and permutation will not be in the exam. Okay. I typically freeze the topics for 1 week before the practice exam, and then 1 week after the practice is the actual exam. Except for the final exam, I don't have the luxury to freeze ahead of time.
Yeah.
Okay, so this is the CNF assignment. Okay, so the first thing is we want to convert everything into CNF first. So we look at the first one, which turns out to be the most difficult one. I'm just writing it on the piece of paper first, then we can switch to paper. Okay, there we go. And then we switch to this slanted paper. Not so slanted anymore. Okay. So we want to say, okay, but how do we convert this into a CNF? The first thing we need to get rid of is the implication, because implication is not even a disjunction, nor a conjunction, nor a negation, so we need to get rid of it. Okay, that's pretty easy. We take the negation of the first part, which is Q or R together with a disjunction, and then we say or the second part, which is just P itself. It looks like we can just dissolve the parentheses, but we cannot, because the negation applies to the disjunction of the first part, so we cannot just dissolve the parentheses. Instead, we have to apply De Morgan's law so that we don't have a negation on the outside. So once you apply De Morgan's law, then you basically negate everything in the inside, and then change the operator from disjunction to conjunction in this case. Is that okay? So if I want to write down how this happens, this is by definition of implication. implication. And this one is De Morgan's law. De Morgan's law. Okay, so now that we have this, we can apply the distribution. So we can now have. I was hesitating because I wanted to see if this is already in CNF. Because if it's already in CNF, then we are done already. But it's not. Okay, because it's not in CNF because the last operation is a disjunction. And then we have one side of the disjunction not being a single variable, but a conjunction. So that's why it's not in CNF already. So okay, let's go ahead and apply that. So we have not Q or P as one component, and then not R or P as the other component. Now it is in CNF. Because it is a conjunction overall, and then each component is a disjunction, and inside each disjunction we only have variables or the negation of variables. So we're good, okay? Switching back to the question itself, the next one is P implies Q, P implies S. Okay, so let's go ahead and do that one too. P implies S. First of all, we get rid of, well, I'm going to write this down too. This is by distribution. Okay, so with this one, it's easier because we just negate P or S, right? This is by definition. So once again, by DEFN of implication. There we go. And we're done. Because even though it doesn't have any conjunction in it, it is already in CNF. Because it's a disjunction that only consists of variables and the negation of variables. It is in CNF already. And the last one is the easiest one. The last one is just S, all by itself, because it is a single variable. It is already in CNF. Okay? So now we have all three CNFs, but the question is asking you to convert all the known facts into a single long CNF. So you have to give me a big conjunction of all of these things. So the final answer, the final CNF that I want to see is going to be this thing, not Q or P, and not R or P, conjunction with the second one, which is this thing here. But now we have to introduce parentheses, and the last one, which is this one here. So this is the actual answer. Yep.
You say that has 4 clauses, right?
It has 4 clauses. Yeah. Yep.
So you just basically make it into a huge long conjunction.
Yep. Yeah, but if you get to the individual one, but just miss the last one, it's going to be minor points, not a big deal. Are there any questions about the answer of the assignment that was due today, earlier? Nope. Okay. So your next homework assignment, which I assigned on Monday, and I changed the due date as well. So it now has the correct due date. It is based on what we already have, but I want you to use proof by contradiction and resolution to prove either Q by itself is a theorem or it is not a theorem. Okay, so either way, give me your conclusion. Is it a theorem of the stuff that we already know about this system? Okay, so 2 things that are important is, one, you have to use resolution as the mechanism to take you from one step to the next, but you also have to apply proof by contradiction to help you determine whether Q is a theorem or not. Is that okay? And just by the looks of it, it would not be a very long process. Yep, it's not going to be very long. I mean, it'll take you like a few steps before.
Can you use the shorthand?
Hmm?
You'll use the shorthand?
Yes.
Okay.
So in this case, you can use the shorthand just like with the previous homework assignment. It kind of makes sense that way, because otherwise you would not be able to copy your own answer to the answer of the new question. So you can use the shorthand as well. Does anyone want me to kind of mention the shorthand again, or you guys got that part? Okay. All right. So that's your new homework assignment. You have 5 days to do it, okay? And I have office hours if you have any questions about resolution or proof by contradiction. Any questions? And the exam is next Wednesday for this class because it's always 1 week after the practice exam. So since we only had the practice exam today, so the actual exam is next Wednesday, which is kind of nice because on Monday I will disclose the solution of the homework assignment. So that will give you a chance to ask questions about resolution and proof by contradiction before we have it in the exam on Wednesday. Okay. Questions? Nope. Okay. So I just want to point out, this is a slight digression, but I think it is related to this class, except, but in a very applicable way. Okay, so there's a concept called random forest or random tree or a bunch of random trees in this case. I just want to introduce the terms. I'm not going to ask any questions about random forest and stuff like that. But this is, currently, this is one of the most common machine learning techniques that people use in data mining. Okay? And it is related to this class in a certain way because it has to do with probabilities. It has to do with building up a tree, a decision tree, and you're basically just observing the frequencies of things happening. Okay, I can give you one really quick introduction. Okay, so let me switch to my document camera here. So let's say we are talking about fatality of car accidents. Okay, in other words, in the end, it has to be something that is true or false. Okay, did someone die? Okay, so the decision tree is basically saying, okay, let's go ahead and differentiate all the cases of car accidents. Okay, and you can choose whatever attribute you want to use to make that decision. Okay, because the only thing you have to do is to say, okay, there are 2 ways to proceed. One way to proceed when the condition is true. One way to proceed when the condition is false. But what this condition is, it's kind of up to you. Okay, you have to tweak it. So the first thing is, is the driver younger than 30 or older than 30? At least 30, okay? So 30 years old, okay? If so, we go to this way. If not, we go to the other way. Then you have to ask, a question again, okay? So you continue to differentiate. So in this case, we say, is the driver male or not? Okay, is the person male or not? So once again, we have true, false here. And if you need additional ways to differentiate, you can ask further questions. But this is called a decision tree in general because you're just asking questions. So let's just say that this is all we need. Okay, this is the entire decision tree. We have 4 leaves at the end. Each leaf is basically something at the bottom of the tree. It is a conclusion. Okay, so given any driver, they have to fall into one of these things. Okay. And let's just say that we only feed drivers that perish in a car accident into this whole thing. Okay? So now for car insurance companies, what they can do is they can go over all the known cases of fatal car accidents and then build up the probabilities of these things. It's just statistics, right? You just run through all the past samples. How many people in a fatal accident are 30 years or older? Okay, then you have probability, X amount here and X amount here. Of the people who are 30 years old or older, how many of those are male? Falling to this category. How many of those are female? Falling to this category. So once again, we have probability here and here. Does that make any sense? Okay. So we're gonna I'll just assign some random probabilities here. So let's say 30% is here, 70% is over here. And then we have 65%, 35%. Let's say we have 55 over here and 45 over here. These are completely made up numbers, okay? So the question is, what can we do with this tree? Well, we can run simulations. So you basically run Monte Carlo simulation. In other words, at each junction, you throw a dice. And you go like, okay, if I just throw a dice and determine which way to go, in the end, what are the probability of ending up in a particular leaf? Okay, that's Monte Carlo simulation. But it is in a way machine learning because the machine originally did not know about the probabilities. The probabilities were learned from samples. Are we doing okay so far with this? So you have different trees, that use different criteria and on different data sets. So now you have multiple trees. Each tree looks kind of like this. And then what you do is you run Monte Carlo simulation on all of these trees to see what is going to happen, to basically help you predict what is going to happen. Because one tree is not always accurate. It can overfit the data points. But when you have multiple trees training on different data, then you have, then they can all vote and say, I think this is going to happen. I think this is going to happen. I think that is going to happen. So they can reduce the effect of overfitting data. So I just want to kind of present this because it's really kind of interesting. It's easy to implement in many, many ways, but it's also used a lot these days in search engines and data mining because people use this to train computers so that they can sort of predict what people are likely to do. If you go online shopping, Amazon, how does it know that, I think you might be interested in these items as well? And sometimes it has accuracy to that, to the recommendation as well. Yep.
So I know random forests are used when there's not, especially when there's not a lot of structure to data. But when you use a random forest, and when you go for some of the more heavy methods like SVMs or, in some cases, neural networks. I know neural networks are becoming much more popular thanks to TensorFlow and the discovery of recurrent neural nets. But I just never know when you're supposed to use which method.
I think sometimes you have to try and find out which one works best.
Then how do you avoid accidentally fitting your method, overfitting the data by just trying a bunch of different methods?
So what you can do is you can train your computer using a particular set of data, but you reserve a larger set for testing purposes. So the stuff they use for testing is never used for training. So after you train your data,
But isn't I just assumed the standard was capable of cross validation. But okay, so you're saying you just want to test on various different. You want to test your algorithm with various different algorithms. Your data with various different algorithms. Okay, sorry.
Well, we can deal with that maybe on a different day. Last time in terms of discrete probability, we talked about combinations and permutations. How many people still have a vague idea of what that stuff was? Okay, very good. So this slide really is just talking about everything that we talked about already, and also using lotto tickets as an example. So we're going to move on to the next one, which is frequencies and probabilities. Let's move on to this one over here first. Okay, how and when to use combination and permutation. Okay, and because I want to move on to this one because it has two concrete examples. So we'll use this example here first to illustrate, the concepts of combinations, permutations, and exponent. When do we use, one or the other? So the problem here is to calculate what are the chances that R out of n people have exactly the same birthday, but the rest of the class they all have different birthdays, unique birthdays. Okay. Are we doing okay so far? So let's say, right now we have 35 students in this class. So the question is, what are the chances that, let's say 5 students out of this entire class share exactly the same birthday, but then the rest of the class, the other 30 students, all have unique birthdays? That's what we're trying to figure out. Okay. So how do you approach this problem? Well, first of all, we think of the omega. Okay, what is the set of all possible outcomes? What do you think is the the set of all possible outcomes. We're dealing with birthdays here, and there are 35 people. So let me switch to the document camera. So I guess I'll stay on the document camera for a while here. Okay, so I'll present the problem. 35 students. What is the omega? The omega would be all possible outcomes. In other words, we're looking for all possible outcomes when we have 35 students in the class, and each student can pick one out of 365 days as the birthday. So what is the cardinality? I don't even bother to look at each individual item in omega because it's going to take a long time to even write one element. So I will just look at the cardinality of omega here. Well, we take a look at one person first, okay? We take a look at myself and go like, how many choices do I have as a birthday? 365. What about the next person? Same, because at this point we are not concerned about collisions or whether people have the same birthday or not. I'm just trying to enumerate all possible combinations of birthdays. So the cardinality in this case is 365 to the power of 35, because each person in the class has a choice of out of 365. Now, only a subset of this is what I am interested in, but this is the baseline. Is that okay? All right. So now that we know that omega, or the cardinality of omega, is 365 to the power of 35, now we need to figure out, okay, out of these many cases, how many of these elements would fit the description that I'm interested in? Okay, so I'll restate what I'm interested in. So I want the case where 5 students share the same birthday. The other 30 have unique birthdays. Okay. So this is my problem. Okay, I want to find a subset of this omega that fits this description. Any 5 students in the class share exactly the same birthday, and then the other 30 students have unique birthdays. But they can be all over the place. Okay, I don't place restrictions as to what those birthdays can be. So now what do we do about this? There are several ways to look at this. Okay, if you read the notes, okay, there are several ways to look at this. So the first one that we can look at, the first way we can look at this is like, okay, so how many unique birthdays are we talking about amongst these 35 people? We have 31 exact birthdays, right? Because we have 30 unique birthdays of the 30 people, but then those 5 people share the same birthday, but that has to be distinct from the other 30 birthdays. Right? Okay, so we say, okay, we have 31 unique birthdays to deal with. We don't know exactly which 31 out of 365 days, but we have 31. Is that okay? But haven't we encountered something that can compute choosing 31 things out of 365? Okay. Do you remember this notation? One way to say this is to say, oh, it's the combination of choosing R items out of N. But the short form of this is N choose to R. Okay, this is N choose R. So in this case, we can apply that and say we have 365 days to choose from. Out of 365, we want to choose 31 of those. So this becomes a number of ways to find 31 birthdays out of 365 days. Are we doing okay so far? Okay, so this is ways to find 31 unique days in a year. Okay. That's a part of what we need, but that's not the actual thing that we need, because now we have 31 birthdays, and then we say, okay, how can we distribute these 31 birthdays amongst 35 students so that we end up with 30 students with unique birthdays and 5 with, the same birthday. So that becomes the next question. Okay? How would you approach that problem? So we have one thing here. We'll just say, okay, we're done with this part here, how to pick the 31 days. But now that we have picked exactly 31 days, how do we distribute those 31 days to the students, 35 students? How about looking at it this way? Out of the 35 students, I'll first choose which 30 have unique birthdays, which automatically locks down which 5 share exactly the same birthday. Would that make sense? Okay. Sort of. So now we're looking at, we have 35 students, and we want to choose either 30 or 5 because they boil down to the same number. So you can, this is exactly the same as that, okay? But we want to find out, we want to give this number a name, okay? Because we are choosing, this is the number of ways of choosing which 30 students have exactly the same birthday. Okay? So this is ways to choose which 30 students out of 35 have unique birthdays. So they are not sharing the birthday with anyone else in the class. But by choosing these 30, I also automatically lock down the other 5 because the other 5 must have exactly the same birthday. Are we doing okay so far with this? Okay, so now what else can we do? We're almost done with this particular question. We got this many ways to choose 31 birthdays. But let's pick one of these, combinations of birthdays. So when we choose one of these, and then we say, well, we can now assign these birthdays. There are this many ways to assign these 31 birthdays to 35 people. Is that okay?
Yeah.
And so this will become the number of ways to arrange birthdays in a way that I'm interested in. But that doesn't give me any probabilities. It just gives me a number. But I wanted chances. I want to know what are the chances that this happens in a class of 35 people. So now I have to say, okay, so we have to divide it by the cardinality of omega itself. Okay, but omega is 365 to the power of 35 in this case. So this becomes the probability of finding a class of 35 students where we have exactly 30 people with unique birthdays, and then the other 5 have exactly the same birthday. Any questions about this? Yep.
Could you just remind me what the notation ends up working out to? The choice notation?
The choice notation? N choose R is the same thing as N factorial divided by N minus R, the whole thing factorial, and times R factorial. And the factorial is, N factorial is N times N minus 1 times N minus 2 all the way down to 1. So I've got to compare that to my actual answer here. Nope, I was actually off by a little bit here. I guess I will have to revisit this, on next Monday. Yep. Mm-hmm.
So you're saying the possible answers is 365 to the 35th power? That's what that.
This is the denominator. But the question is, in the numerator, I think I might have made a mistake either today in class or in my notes about this one here. Because in my notes, I was using a permutation instead of combination. So I have to think about this a little bit to see whether it should be a permutation or whether it should be a combination. In other words, is ordering important in this case? That's the question. All right. And I think the permutation is probably the correct one, but I'll explain this one on next Monday. All right. So you guys have homework assignment due on Monday, so make sure you work on it. Yep.
I like that CNF assignment, solve